Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the meaning of the second derivative and what does it say about fx. So what we have here is concavity test, and the rules are given as follows. So for the first one here, if the second derivative is greater than 0 on an interval, then the graph of fx is concave upward on that interval. Now for the second one is that if the second derivative is less than 0 on an interval, then the graph of fx is concave downward. So the definition of concave upward and concave downward are given in this purple box here. It is called concave upward if the graph of fx lies above all of its tangents on that particular interval. And it is called concave downward if the graph of fx lies below all of its tangents on a particular interval. And I think the best way to understand these statements here is by looking at the simple diagram given on this slide. So if you can see here, what we have is the red line. So the red line is the graph, the red line is fx, and for the first picture that you have here, so this is the first picture that you have, you can see that the red line here is above the blue line. So the blue line is the tangent line. So for all its tangents, you can see that the red line here is above all its tangents. So we call it concave up. Similarly for this one, so this is the second situation here, you can see that the red line here is above all of its tangents, and so this is the idea of concave upward. Now of course the graph can be either decreasing in nature, so it is going down, or it can also be increasing in nature, so it's going up. Right, next let's look at the third situation here. So the third situation here, as you can see, this is the red line, the original graph fx here. It is below all its tangents. So the tangent lines here are represented by the blue lines. So the red line here is below all of its tangents. Therefore, we say that this is concave downward. Similarly for this one, this is the fourth situation. You can see that the red line here is below all of its tangents, and so this is concave downward. And as you can see here, this is an example of a graph that is decreasing in nature, so it's decreasing in that interval, and this is a graph that is increasing in that particular interval. Okay, right, next, following the idea of concavity, a point P on a curve fx is called an inflection point if the curve changes from concave upward to concave downward, or from concave downward to concave upward at P. So this idea of inflection point is the same idea, more or less the same idea of critical point, which you have seen in the first derivative. Okay, now let us recall what is critical point. So critical point, based on the first derivative, it is the point where the graph changes direction. So critical point is the point where the graph changes direction. For example, this could be the critical point because the graph changes direction from going this way to going that way. Okay, so it is you can see that based on the slope of a tangent line, so the tangent line would be like this, going downwards. But for this one, after this critical point here, the direction is changed to going upwards. So this is a positive slope, this is a negative slope. Now similar to that idea, for the second derivative here, we have what we call the inflection point, where the curve is changed from either concave upward to downward, or from concave downward to concave upward. And to visualize what is inflection point, let us consider this first graph that we have here. So you can see that this is the point, this could be the point, the inflection points, where you can see that the graph here changes, the curve changes from, for example, this one. You can see that this is concave upward because the graph is above the tangent line. And for this one, this is concave downward because the graph is below the tangent line. So therefore, since the curve changes from being concave upward to concave downward, then this could be the inflection point. So similar to this one, for example, I can select this point, and if I construct the tangent line, it will be like this. So you can see that clearly the curve here is below the tangent line, and therefore we call it concave downward. And for this one, if I select this point here, I know that the tangent is going to be like this. And so this is the curve here that you have is above the tangent line, so we call it concave upward. So based on this, the curve changes from concave downward to concave upward, and therefore somewhere in the middle here is the inflection point. Sometimes the inflection point is not as clear as this one, because this is the inflection point where the area here is a bit flat. You can see that the line here is a bit quite flat. But for this one, the inflection point is somewhere here. This is a bit different. Now it is somewhere here because for this first curve that we have here, this is the idea of concave upward. Now why is that so? Well, we can go back to the graph that we have here, and you see that if I combine this curve with this curve, then both of these two curves here represent the idea of concave upward. So this is what is given by this one. So concave upward. Now similarly, if I consider this part and this part here, this is the idea of concave downward, as represented by having this curve. And if you consider taking this curve and combine it on this point here, so you will get a curve that looks similar to this one. So this is this area or this interval is the interval where the curve is concave downward. All right. Now there is also a specific test that we call the second derivative test, and this test is also to determine whether a point is a local minimum or a local maximum. So this is the second method that you can use, or the alternative method that you can use to determine whether the point is a local minimum or a local maximum. So the rules are given as follows. So for the first one is you have to find what is the critical point, such that when you substitute into the first derivative, so this is the first derivative, the answer is 0. And if you substitute this point C into the second derivative, the answer will be greater than 0, which is a positive value. And if this is true, therefore that point is a local minimum. Now similarly, if you manage to find what is C, and you substitute C into the first derivative and it equals to 0, and the next step is if you substitute C into the second derivative and the answer is less than 0, therefore that function has a local maximum at C. So this is the alternative method, and you can use it as well if you don't want to use the first derivative test. Now the point A here can be visualized as such, okay, as given by this one. Now recall what is the meaning of second derivative greater than 0. So as you can see in this slide, when the second derivative is greater than 0 on that interval, that means the graph of that is concave upward. So back to this statement here, the rule stated that the second derivative, when C is substituted into that, and if the answer is 0, therefore we know that this corresponds to having the curve that is concave upward. And if the curve is combined, so this is concave upward in a decreasing manner, and this is concave upward in the increasing manner. And if you combine that, you will get a point somewhere here, which is the local minimum. So I think based on my explanation just now, I'm sure you can visualize how point B may be represented. Okay. Alright, I think that's all for now. Thank you very much for watching. I will see you in the next video with an example that illustrates all the information that you have seen in this video, plus what you have learned about the first derivative. Thank you very much for watching.